Hi everyone, we are going to talk about mixture of Gaussians. The mixture of Gaussians is a parametric model that can be used to find clusters in our data, estimate the density function of the distribution of our dataset, and sample from that estimated density. Before we start discussing the details of the mixture of Gaussians algorithm, let's talk about some important properties of the Gaussian distribution. The Gaussian distribution has two parameters, the mean and the variance. In one dimension, this is its density function. The mean is denoted by mu, and the variance is denoted by sigma squared. The generalization of the one-dimensional Gaussian distribution to multiple dimensions is called the multivariate or multidimensional Gaussian distribution. In d dimension, it has a d-dimensional mean vector mu and a covariance matrix sigma with size d times d. Often we use this calligraphic n with subscript x, parameters mu and sigma to denote the density function of this multidimensional Gaussian distribution at a location x. This expression is the density function of the multivariate Gaussian distribution, and this is how the surface of a multivariate Gaussian distribution looks like. Here, this expression means the determinant. That is, we have to take the determinant of 2 pi times sigma. If a random variable x has a multivariate Gaussian distribution with a covariance matrix sigma, then sigma ij, the ij element of the covariance matrix, indicates how much the dependence is between xi and xj. If this quantity is 0, then xi and xj are independent. If it's a positive number, then they are positively correlated. If it's a negative number, then they are negatively correlated. In this example, sigma 1, 2 is 0.8, which indicates that x1 and x2 random variables are positively correlated. I created this Jupyter notebook demo on Google Colab to visualize the density function and the level sets of the density function of a two-dimensional Gaussian distribution. A level set is a set of points which have the same density values. Let's quickly look at this code that can help visualize the level sets of a Gaussian distribution. First, we import some modules and functions that we will need later. We will import the matplotlib package, the plotly package, pandas, numpy, and the multivariate normal function from scipy. Then we set the random seed to 0 just to be able to reproduce all the results here. Then we set up the mean vector mu of the Gaussian distribution and its covariance matrix. Then we create this variable Gauss that will let us sample points from this Gaussian distribution with mean vector mu and covariance matrix sigma. We will generate 400 sample points, and we use this RVS method of this Gauss object to generate n samples number of points. We generated these points. Now we can use matplotlib to plot these points. We will create a two-dimensional scatter plot of the dataset. And here you can see all the 400 generated points. Now let's look at the level sets of this Gaussian distribution. It's very easy. After creating this multinormal instance, we can just use the .pdf function to be able to evaluate the density function at any location. We create a mesh grid, and then we call this pdf function on the locations of the mesh grid. And then we can use the contour function to create a contour plot of the density function. And you can see here, these curves show some of the level sets of the density function of this Gaussian distribution. We can also have a three-dimensional plot of the level sets as well, and for that we could use the contour 3D command. And if you do that, then we would get this figure here. The only little problem with matplotlib that it's not interactive, so I cannot just rotate and zoom into this plot. If we want to be interactive, then we need to use other toolboxes. So here I'm going to use Plotly for that. So again, let's create a two-dimensional mesh grid. This z grid variable contains the z values of the density function at any location x and y. The code in this cell is just a quick demonstration about how we can visualize the surface of the density of a multivariate Gaussian distribution. We just have to create a figure and set the data of that figure to this surface object, where we specify that we want to show some contours, where the contours will start, where they will end, and what should be the distance between the contours. We can set up title, we can set up what should be the width and height of the image. And then it creates this plot. Here you can see the contours of the level sets of the density of this two-dimensional Gaussian distribution. A nice property of Plotly that it's interactive, so I can just now rotate this density function. We can also show scatter plot in this function, and we will do that in a second. So I just add a three-dimensional scatter to the previous code, and then as you can see here, it's the same code as before, but now we can see the scattered data as well. All right, so this was just a quick demo to show how you can visualize level sets in a Jupyter notebook using matplotlib and Plotly toolboxes. Here is a scatter plot of some samples from a two-dimensional Gaussian distribution. In the following demonstrations, I will often show the level set of the density functions of these normal distributions, because this way we can easily see the mean and covariance of the distribution. After this short introduction, we are ready to discuss applications and learning algorithms for the mixture of Gaussians model. This link points to a Google Colab Jupyter notebook that contains the code of some of the algorithms that we will discuss now. Given a data set like this one, the goal of the mixture of Gaussians density estimation algorithm is to fit a mixture of Gaussians to the data. For example, in this case, if we fit 3 two-dimensional Gaussians to the data, then this is how the optimal fit looks like. The algorithm has to find the correct mean and covariance matrices of these clusters, and we will also have to correctly estimate the proportion of how much percentage of the data belongs to the first, second, and third Gaussian distributions. The distribution of the data set can be more complicated than in the previous case. For example, here it's less obvious what the Gaussian components should be, but you can see that the algorithm made a reasonable estimation. These are the estimated level sets of the density after we fit 6 Gaussian distributions to the data. Let's assume for a moment that we already estimated the parameters of these Gaussian distributions. First, we will discuss how to generate more sample points from this mixture of Gaussians model if we already know these parameters. Then we will study how to do clustering with this model, assuming again that the parameters of this mixture of Gaussian model are already known. After this, we will learn how to estimate these usually unknown parameters from the data. First, let's see how we can generate more data from a mixture of Gaussians model assuming that the parameters of this model are known. We are given k Gaussian distributions. We call them the Gaussian components of the mixture of Gaussians model. The parameters of these k Gaussian distributions are mu1, sigma1, and so on, mu k, sigma k. Here, mu I is the mean and sigma I is the covariance of the ith Gaussian distribution. We also need a discrete distribution that specifies the probability of selecting these Gaussian distributions. The parameters of this distribution are denoted by pi1, pi2, and so on, pi k, where pi I denotes the probability of selecting the ith Gaussian distribution. Each pi I is a non-negative number and they sum to 1. After introducing this notation, the data generation from a mixture of Gaussians model is very simple. First, we choose a component with probability pi I, and then we generate a random sample from the ith Gaussian component which has mean mu I and covariance sigma I. This is how we can generate one random sample point from the mixture of Gaussians model. If we need, say, 100 points, then we just repeat this process 100 times. Here is a short video about this data generation process. We generate random samples from a mixture of 3 Gaussians. It's very easy to write up the likelihood function of a data set generated from a mixture of Gaussians model. Let's assume again that we have capital K Gaussian distributions. The first step of the data generation process is to select one of these Gaussians. Let the selected Gaussian component be denoted by y. So if y equals I, it means that we selected the ith Gaussian component. The probability that y equals I, that is, the ith component got selected, is denoted by pi I. After we selected a Gaussian distribution with mean mu I and covariance sigma I, we will use this distribution to generate a random point x. So the conditional distribution of x given that y is I is just a Gaussian distribution with mean mu I and covariance sigma I. Therefore, the density of x is just this expression here. We select a component I with probability p y equals I, which is pi I, and then we use this component to generate a sample from this Gaussian distribution with mean mu I and covariance sigma I. Now, let's discuss how to use the mixture of Gaussians model for clustering. Assume that all the parameters of the mixture of Gaussians model are known. I denote these parameters with theta. These parameters include the mu1, mu2, and so on mu k cluster centers, the sigma1, sigma2, and so on sigma k covariance matrices, and the pi1, pi2, and so on pi k cluster proportions. We know that px given y equals I is a Gaussian density with mean mu I and covariance sigma I. We denoted the probability that y equals I with pi I. This is the probability that we selected the ith cluster. For a given x, we want to decide which one is that cluster where point x belongs to. To solve this problem, we just have to calculate the probability that y equals I given x for all I, where I goes from 1 to k, and then we need to select that I where this is a maximum. Let's calculate these probabilities. Using the Bayes rule, we can calculate Py equals I given x as this expression here. Since the denominator doesn't depend on I, we can ignore that in this maximization problem. Here, the first term is Gaussian, and the second term is just pi I by definition. Therefore, we just need to calculate this term for all I where I is going from 1 to k, and then we need to choose the maximum value. So as you can see, clustering with the mixture of Gaussians model is very simple if we already know the parameters of this model. Now, let's discuss how the decision boundary between any two clusters looks like in this clustering problem. Again, let's assume that all the parameters of this mixture of Gaussians model are known. For a given x, we want to decide if x belongs to cluster I or cluster J. To be able to answer this question, we can just simply calculate the log of the probability ratios, that is, the log of the probability that y equals I given x divided by the probability of y equals j given x. If the ratio is bigger than 1, that is, the log of this ratio is positive, it means that point x belongs to cluster I, otherwise point x would belong to cluster J when we can only decide between these two clusters. Using the Bayes rule, we can rewrite both the numerator and the denominator of this fraction. As you can see, the PEX terms cancel out. The probability that y equals I is just pi I by definition. Similarly, the probability that y equals j is just pi j by definition. And the conditional probabilities of x given y are just Gaussian distributions. Therefore, the log of these probability ratios is just this expression. Since inside of this log function there is a product, we can greatly simplify this expression. Log a times b is just log a plus log b. Therefore, this expression is just the sum of these two terms. Since exponential a divided by exponential b is just exponential a minus b, we can also simplify this expression. Here, the log function cancels the exponential function. This is just the difference between two quadratic terms, and it's easy to see that we can simplify it further. Here, the first term and the last two terms don't depend on x, they are constant, and we can denote them by c. So finally, we have that the log of the ratios of the probabilities is just this quadratic expression. So the log of the ratios of these conditional probabilities is just this quadratic function. Therefore, if sigma I is not equal to sigma j, then the decision boundary between any two clusters is a quadratic function. It might look something like this. However, if sigma I equals to sigma j, then the quadratic term cancels out. Let w denote this expression, and c is the constant term as before. Now, the log of the ratio of these probabilities is just the x transpose w plus c linear function. So if c plus x transpose w is positive, then x belongs to cluster I. Otherwise, x belongs to cluster J. In this case, the decision boundary between the two clusters is a linear function, and if we have three clusters, then the decision boundaries might look like this. So far, we assumed that the parameters of the mixture of Gaussian models are all known. Now, let's investigate how we can learn these parameters from our data. So what can we do if we don't know the parameters? We could try to do a standard maximum likelihood estimation. Let x1, x2, and so on xn denote our training set, and let theta denote all the unknown parameters, the mu1, mu2, and so on mu-k cluster centers, the sigma1, sigma2, sigma-k covariance matrices, and the pi1, pi2, and so on pi-k cluster proportions. The likelihood function is just this expression. We need to maximize this in theta. Let yj equals I denote the event that xj was generated from the i's Gaussian distribution with mean mu I and covariance sigma I. The p xj given theta probability can be rewritten with the joint distribution of yj and xj. We just need to marginalize out yj, as you can see here. Since the joint distribution of y and x, pyx, is just py multiplied by p x given y, we can rewrite this expression to this form, which is great since here we know all the terms. The first term is just pi I by definition, and the second term is just the density of a Gaussian distribution with mean parameter mu I and covariance sigma I at a location xj. This is what we need to maximize in theta. How can we maximize this expression in theta? We could just calculate its derivatives with respect to the parameters and then try to find those parameters when this derivative is 0. This is very difficult because the equations are nonlinear and there are no closed form solution for these. A second way to maximize the log likelihood is just do a gradient ascent on it. This is doable, but it's often very slow. And the other difficulty is that we should also satisfy our constraints, such that the covariance matrices have to be positive semi-definite, for example, and the pi I parameters have to be non-negative and they have to sum to 1. It can be very tricky to satisfy all these constraints with gradient ascent. The third way is to do expectation maximization, which is also known as the EM method, and this is what we are going to discuss now. Let's quickly review our goal. We are given a data set, x1, x2, and so on xn. The data set is denoted by D. Each of these data points belong to a cluster. The cluster assignments are denoted by y1, y2, and so on, yn. For example, if y3 is 5, it means that x3 belongs to the fifth cluster. We don't know these cluster assignments. We will need to estimate them from our data. Our unknown parameters are collected in this variable theta. We need to estimate the mu, pi, and sigma parameters. The goal of the maximum likelihood estimation is to find that parameter theta that can maximize the log likelihood function, that is the log of the probability of the data given the parameters theta. First, we will just discuss how the expectation maximization or EM algorithm works and what the main steps are. Then later we will discuss why these steps make sense. So our goal is to maximize the log likelihood function. The EM algorithm consists of two steps: the expectation step or E step and the maximization step or M step. It is an iterative algorithm where after the expectation step, we do a maximization step, and then we repeat this process, going back to the expectation step and then maximization steps again, and we do this till the algorithm converges. In the expectation or E step, we just create this function. This function is denoted by Q. It has two arguments, theta and theta at iteration t-1. Theta denotes the current parameters, and theta at t-1 denotes the parameters in the previous iteration at time step t-1. The function Q is simply the conditional expectation of the log of the joint distribution of y and the data d given the parameters theta. The tricky part is that in the conditional expectation, we condition on the data and the parameters at the previous iteration t-1. Using the definition of conditional expectation, we can also simply just write this Q function with this integral. This is the integral of the product of p, y given the data d and parameters theta at time step t-1 multiplied by the log of the joint probability distribution of y and data d given the parameters theta. We will discuss later why we define this function exactly in this way, but for now what you should see that this function indeed has two arguments, theta and theta at the previous iteration t-1. The m step or maximization step is simply trying to maximize this function q in its first argument theta. At this point, it might not be clear why this e step and m step do something reasonable. To make it clear, we will state our main theorem. We can prove that during the EM algorithm, the marginal likelihood is increasing, or at least stays the same. That is, p data given theta at time step t is always smaller or equal than the probability of the data given theta at time step t+1. So if we want to maximize the likelihood function, we just need to keep repeat these EM steps till convergence. We will see that in the mixture of Gaussians problem, the E steps and the M steps have very simple forms, and they are very easy to implement. The integral in this conditional expectation can be found in a simple closed form. The solutions to this maximization step can also be found in a simple closed form. So at the end, the algorithm for estimating the parameters of the mixture of Gaussians will be very simple. We will see that soon. As we discussed, this is the general form of the Q function. Let's apply this to our mixture of Gaussians parameter estimation problem. We want to estimate the parameters of a mixture of Gaussians model. In our case, y denotes y1, y2, and so on, yn, where yj is an integer number between 1 and k, and it shows which Gaussian distribution generated xj. Since yj is an integer, therefore this integral here just becomes a sum. The deta d is just a collection of x1, x2, and so on xn, so we can rewrite the function q into this form. We assume that the data points were generated independently, so this probability here will be just the product of the marginal distributions of the yj, xj quantities. The log of a product of some items equals the sum of the log of those items, therefore we get this expression. Now observe that in this log function there's only one yj, therefore the other yi quantities marginalize out in this sum. So this expression can be further simplified. Yj is independent from the other xi quantities, so we can simplify this even further. And finally, we arrived at this specific form of the Q function, and this is what we will use to estimate the parameters of the mixture of Gaussians. Now we know that in the mixture of Gaussians case, this is how the function Q looks like. We will need to maximize that in theta t. To be able to do that, we need to calculate these p y given x theta conditional probabilities. It's very easy to calculate these using the Bayes rule. The Bayes rule simply says that py given x equals to px given y multiplied by py divided by px. We know that these probabilities have to sum to 1, therefore this normalizing denominator term must have this form. And here we know all the terms. Px given y is a Gaussian distribution, py equals I is just pi I. So let's plug them into this form and then we are done. This is quite a long expression, but all quantities here are known and it's very easy to calculate them. From now on, this quantity will be denoted as Rij at iteration t-1. The intuitive meaning of this distribution is that here we try to assign a cluster label to point xj, but we do it in a soft way. For each cluster I, there are some probabilities that xj belongs to cluster I, and these probabilities have to sum to 1. Using these Rij quantities, we can rewrite the function q. Since the joint distribution of p, y, and x is just the product of px given y and py, we get this expression. We know that px given y is Gaussian, and py equals I is just pi I, and therefore we have this expression. We will need to maximize this in parameters theta t. That is, we need to maximize this in mu t, sigma t, and pi t. Let's maximize this in mu t first. Because of this log function, many terms here will be just constant in mu t, and we can ignore those. Then our objective function will be just this. In the m step, we need to calculate the derivative of this with respect to mu t and find that mu when this derivative is 0. The derivative is simply this expression, and from this we get this here, and it's very easy to find the optimal solution of this in a closed form. So the m-step update of mu it is just this expression here. In other words, mu is just the weighted linear combination of the data with these weights. Similarly, we could calculate the update rule for sigma I and pi I as well. So as you can see, all the updates for mu, sigma, and pi are very simple when we do expectation maximization. There are no learning rates or other tunable hyperparameters, just a few simple parameter update rules. Let's see how these update rules work in practice. Here is a two-dimensional data set. We want to fit 3 Gaussians to this data. For each data point, the p, y given x, theta conditional probabilities are indicated by these pie charts placed in the locations of the training points. We use red, green, and blue colors to visualize the probabilities of being assigned to the red, green, and blue clusters. As you can see, in the first iteration, for many points, the algorithm doesn't know how to best cluster these points, and for some of the training points, it just assigns roughly the same probabilities to all clusters. As we update the parameters with the EM iterations, the algorithm finds better and better clusters. The expectation maximization method found good parameters for this mixture of Gaussians problem, and it was able to cluster the points well. Most points are confidently assigned only to one cluster. So far we discussed what the expectation and maximization steps are in the EM algorithm, but we haven't proved why those steps would make sense at all. Now we will study the theoretical properties of the EM algorithm and prove that the iteration of these expectation and maximization steps indeed improves the likelihood function. The expectation maximization is a general algorithm that can deal with parametric machine learning problems that have hidden data. There are many machine learning problems with this property, for example, hidden Markov models or linear dynamical systems, but we study expectation maximization in the context of unsupervised clustering with Gaussian mixture models only. EM is an optimization strategy for objective functions that can be interpreted as likelihoods in the presence of missing data, for example, the cluster assignment in the mixture of Gaussians model. In the mixture of Gaussians example, we noticed that the EM updates are actually simpler than the updates in the gradient descent method. We don't need to choose step size, for example. EM is an iterative algorithm with two linked steps, the E step or expectation step, where we fill in hidden values, that is, we calculate the probability of y given x quantities. And there's an M step where we apply standard maximum likelihood method to the completed data, that is, to the joint distribution of y and x given the parameters theta. We will prove that this procedure monotonically improves the likelihood function, or in worst case, it leaves it unchanged if, for example, if it's already converged. Let's quickly summarize our goal. We are given a data set x1, x2, and so on xn, and this data set is denoted by D. Each of these data points belong to a cluster. These cluster assignments are denoted by y1, y2, and so on, yn. We don't know these cluster assignments. We will need to estimate them from our data. Our unknown parameters are collected in this variable theta. We need to estimate the mu, pi, and sigma parameters. The goal of the maximum likelihood estimation is to find that parameter theta that can maximize the log likelihood function, that is the log of the probability of the data given all the parameters theta. We will try to increase the log likelihood function with the expectation maximization method. It has two steps. In the E step, we create this function q. It is a conditional expectation given in this integral form. In the M step, we maximize it in its first argument. We will prove that during the EM algorithm, the likelihood function of our data is increasing, or at least stays the same. So the probability of our data given the parameters theta at iteration t is always smaller than or equal to the probability of our data given the parameters at the next iteration t plus 1. Before going into the details of the expectation maximization method, let me try to illustrate it. We are given a log likelihood function, that is the log of the probability of our data given the parameters theta, and we need to maximize this function. It is difficult to maximize it directly, so instead we will do a trick. Let's assume that at iteration t, we already have an estimate theta t. In the next iteration, we want to create a theta t plus 1 that will be better than the current theta t. We will create another function f that will be a lower bound on the log likelihood function. This function will have a parameter q, and function f is constructed in such a way that for any parameter value q, fq theta is always smaller than or equal to the log of the probability of our data given theta, that is the log likelihood value at theta. The function f with parameter q1 is shown with this blue curve on this figure. For another parameter q2, function f might look like this. You can see It is again smaller than the log likelihood function at any location theta. At iteration t, the current parameter is theta t. We will try to find the parameter q for this function f such that fq would touch the log likelihood function from below in theta t. We denote this parameter by q star, and fq star is shown with this curve. This will be the expectation step of the EM algorithm. After we found this q star value, we can maximize fq star in theta. Let this red dot show its maximum. The location of the maximum is denoted by theta t plus 1, and this will be the maximization step of the EM algorithm. Since function f touched the log likelihood function, then we increase this function f, and f is always below the log likelihood function. Therefore, the log likelihood function at theta t plus 1 will be higher than it was at theta t. An interesting point that I didn't mention yet, that the parameter q in this function f will not be a typical finite dimensional parameter vector, but instead it will be a density function or a probability mass function of a distribution. After this illustration, let's see the details of the EM method. We will need the definition of the Kullback-Leibler divergence. For any density functions p and q, the Kullback-Leibler divergence between densities p and q is defined by this expression, integral p times log p over q. It's easy to prove that this divergence is always non-negative, and it is zero if and only if p equals q. So in some sense, it measures how far p is from q. The distributions of p and q actually don't need to be continuous. The Kullback-Leibler divergence has a discrete version too. In this case, we use probability mass functions instead of density functions, and instead of using an integral, we just write a sum. From now on, I will use the integral version, but you should know that we can always use the discrete version when needed. Our goal is to maximize the log likelihood function in theta. We will make some manipulations on this log likelihood function, and these manipulations will help us define that function f, which will be a lower bound on this log likelihood function. Let y be a random variable with an arbitrary distribution q. If y is continuous, then this function q denotes its density function. If y is discrete, then q denotes its mass function. I will often just say density function q at the location y, but you should understand that when the random variable y is discrete and we use this q function in an integral, then this integral just becomes a simple sum. Since the integral of q is 1, we can just multiply the log likelihood function with it. Moreover, since the log likelihood does not depend on this y, therefore we can move this log likelihood term into this integral. Here, I just multiplied the log likelihood with qy divided by qy, which is just 1. So it seems it does nothing, but actually it will help us soon decompose the term inside the log function in a useful way. Now, since pyd is just pd multiplied by py given d, we have that the probability of the data given the parameters theta equals the probability of y and theta d given the parameters theta divided by the probability of y given the data and the parameters theta. We can plug this back to the previous equation and then get this form. This is why we did these manipulations on the log likelihood function. Now, as you can see, inside the log function, there's a product of 4 terms, and therefore, using that log a times b is just log a plus log b, we can decompose and simplify this expression. Now, this term is just the Kullback-Leibler divergence between Q and Py given theta d and parameters theta. Now this term here is just the entropy of the distribution Q. For historical reasons, this term is the so-called free energy. This free energy function is denoted by F. It has a parameter Q, which is a distribution. Therefore, for any distribution Q, the log likelihood function of the data at a location theta equals to the free energy function at theta plus this Kullback-Leibler divergence. Here, the free energy function with parameter Q at the location theta is just this integral plus the entropy of the distribution Q. So we know that for any distribution Q and parameter theta, the log likelihood function has this decomposition. Since the KL divergence is always non-negative, from this we can see that the log likelihood is always at least as big as the free energy. So indeed, we were able to construct a function f that always lower bounds the log likelihood function. Here I'm illustrating this function f that's always below the log likelihood function. As we mentioned earlier when we discussed the intuition for the EM algorithm, in the location theta t, we want to select a Q star distribution such that with this Q star parameter, FQ star will touch the log likelihood curve from below. Let's choose Q star y to be the conditional probability of y given the data set D and the parameters theta t. With this Q star function, this KL divergence is 0, and therefore indeed the log likelihood function is the same as the free energy in this location theta t. Here I'm illustrating how this function fq star touches the log likelihood function from below at a point theta t. As a reminder, this was the Q function in the E step of the EM algorithm. Using our notation, we can also write the Q theta t function as the free energy at theta, where Q is set to the conditional distribution of y given the data set D and the parameters theta at iteration t, minus the entropy of this distribution. So, as we discussed, the log likelihood function has this decomposition, and it is lower bounded by the free energy. We defined this uppercase Q theta t function by this expression. We also noted that it can be rewritten with the free energy function and the entropy. From this, it immediately follows that the free energy function is just the sum of this Q theta t function plus the entropy. Finally, we are ready to prove that the EM algorithm indeed increases the likelihood function, or in the worst case, at least it doesn't change its value. We already discussed that in the E step, we set the lowercase q distribution to the Py given theta d and theta at t, and then the free energy function f will touch the log likelihood function from below at the point theta t. Using this above mentioned identity for the free energy function, we can rewrite this term with the function q and entropy h. In the M step, we need to maximize this function q in its first argument. The location of that maximum is theta t plus 1. Therefore, this expression can be upper bounded using q theta t plus 1 theta t and the entropy term. Now, using again our identity for the free energy function, which says that the free energy is just the q function plus the entropy, this expression is exactly this specific free energy. Looking at the first line on this slide, the decomposition of the log likelihood with free energy and Kullback-Leibler divergence, we have that this free energy is just the log likelihood at theta t plus 1 minus this Kullback-Leibler divergence. But now, since the KL term is non-negative, we can see that indeed these EM updates increase the log likelihood function, or in the worst case, they just keep the value the same. This is what we wanted to prove. Let's summarize what we discussed so far. For any theta t and distribution q, the log likelihood function at theta t can be decomposed as a sum of this free energy function and this Kullback-Leibler divergence term. In the E step, we set distribution q to the conditional distribution of y given the data d and the parameters theta at iteration t. So the KL term becomes 0 and f theta t is the same as the log likelihood function. Then we maximize this function in the m step of the EM algorithm and get theta t plus 1. In each iteration, the EM steps improve on the log likelihood function, and eventually we converge to a local maximum point. We should also know that depending on the initializations of the algorithm, we can get stuck in bad local optimum points. So in practice, we might need to use multiple randomized initializations. Here on this figure, you can see that based on the initialization, either we converge to this local optimum point or to this one. We discussed that EM is an optimization strategy for objective functions that can be interpreted as likelihoods in the presence of missing data, such as the cluster assignments in the mixture of Gaussians model. The expectation maximization is an iterative algorithm with two linked steps. In the E step, we fill in the hidden y values using inference. That is, we calculate this q star y distribution, which was the conditional distribution of the hidden values y, given our data d and the parameters at iteration t, theta t. In the M step, we wanted to maximize the joint completed log likelihood, the log of the probability of the hidden values y and our data d, given the parameters theta. Since y is unknown, therefore instead of directly maximizing this joint completed likelihood, we maximized the expected value of that. We also visualized the steps of the EM method. In the E step, we lower bounded the likelihood function with the free energy function, and in the M step, we maximized this lower bound. We proved that this procedure monotonically improves the likelihood. We also showed an application of the expectation maximization algorithm for the mixture of Gaussians model. In this Google Colab website, you can find a demo Jupyter notebook code that reproduces the parameter estimation steps in the mixture of Gaussians model. We will discuss this code now. This is a simple demo code for learning the parameters of the mixture of Gaussians model. First, let's connect, and then import a couple of libraries that we will need, such as the matplotlib, numpy, and scipy. K denotes how many Gaussian distributions we want to fit to the dataset, and D denotes the dimension of the Gaussian components. So in this case, we try to fit 3 Gaussians, and each of them is 2-dimensional. This function creates a dataset. The dataset will be a mixture of 3 Gaussians. Mu1, sigma1 denotes the parameters of the first Gaussian. Mu is the mean, sigma is the covariance matrix, mu2 is the mean of the second Gaussian, sigma2 is its covariance matrix, mu3 is the mean of the third Gaussian, and sigma3 is its covariance matrix. we generate 200 points from the first Gaussian, 400 points from the second Gaussian, and 600 from the third Gaussian, and then we shuffle all these points. We create this function, and then we generate 1200 points using this function. Each point is two-dimensional. This variable x denotes our data set. It's a matrix with 1200 rows and 2 columns. And samples will denote the number of sample points. In this case, it is 1200. We create a scatter plot to visualize our data set using just the scatter command from matplotlib. And here you can see our data set. This is 1200 points. Each point is two-dimensional. Here you can also see the 3 Gaussian components. We will try to learn the parameters of these Gaussian components. We will try to learn their mean and covariance matrix, and also pi1, pi2, and pi3. To start running this algorithm, we will need to initialize its parameters. So we will initialize mu, which will contain mu1, mu2, and mu3. Each of them will be a two-dimensional vector. So mu altogether is a 3 by 2 matrix. We also need to initialize the covariance matrices, and we will just let this covariance matrix to be a diagonal matrix with diagonal elements 2.0. Then we initialize pi's. We initialize them uniformly, and as we discussed, pi just contains the proportions of the 3 Gaussian components. So we define this function, and then we call this function. And you can see it created the mu, mean vectors, the cov tensor, which contains the 3 2 by 2 covariance matrices. And we also created this pi vector, which is just a 3-dimensional vector. This one is the matrix of mu's. It's a 3 by 2 matrix. This is mu1. The first row is mu1, second row is mu2, third row is mu3. Then we created 3 2 by 2 covariance matrices. You can see the first one here, second one here, third one here. And finally, we created pi probability vector. It's just a uniform 3-dimensional vector. The next function will be useful to visualize our data set as a scatter plot, and it will also show the level sets of the Gaussian components. So here we create the scatter plot, and then we create a mesh grid where in each of these locations x, y, we will calculate the density values. We will regularize the covariance matrices a little bit just to make sure that they are easy to invert. So we'll just add this small number times an identity matrix to each of the covariance matrices. Then for each of the Gaussian components, we calculate their density with a given mean vector and covariance matrix, and then we visualize the contour plots of that Gaussian matrix, and we will do that for all the 3 Gaussian components. So let's see how it works in practice. We define this function, and then we can plot the scatter plot of our data set with the 3 Gaussian components. And here you can see our initial guesses for the Gaussian components. They are not that good. These are the 3 randomly guessed mean vectors, and the Gaussian components have identity covariance matrices. We want to run the EM updates, and then hopefully these Gaussian mean vectors will converge to the right mean vectors, and similarly the covariance matrices will also converge to the right covariance matrices of these Gaussian components. First, we will run a E-step in the expectation maximization algorithm. And in the E-step, we just need to calculate these quantities, the posterior distribution of the cluster assignments given a vector xj and the current parameters. We need to calculate these probabilities for all I and all j, and we put them into this matrix whose ij's elements is Rij. This is the calculation for this expression, and here you can see how we update each of the ij's element. First, we just calculate the numerator, and then we normalize it with this denominator. After the E step is done, we can do the M steps, and the M step just calculates these quantities, the mu, sigma, and pi. These will be the values in the next iteration, and we calculate them with those Rij terms that we just calculated before, and also we use xj to calculate the mean and the covariance matrices. So first we calculate the weights, these Wij quantities. After it's done, then we can calculate the mean as a weighted linear combination of the xj vectors with these Wij quantities. After the means are calculated or updated, then we can calculate the covariance matrices. Similarly, the covariance matrix is just a weighted sum of these xj minus mu transposed xj minus mu quantities. Here we calculate those covariance matrices. And finally, we can update the pi vectors, which is very simply just this expression here. So these are the updates for the pi's. When we are done with all these, then using these new updated parameters, we can calculate the log likelihood function of our data set. That happens here. I'm visualizing the new updated covariance matrix and the new updated pi's. And finally, we can show what are the updated means and updated covariance matrices. And you can see them here. And they are much better than the previous random guesses. They are still not perfect, but they are moving to the right direction. This mean already looks good. This mean already looks good. This mean is not that good. This covariance matrix is not that good. But we will repeat these EM updates, and eventually these covariance matrices and mean vectors will converge to the right locations. So now the E step is done, and we can go back to the M step to do this iteration again. I put everything together into this class GMM. It shows the dimension of each Gaussians, what the data set that we are going to use, what are the parameters that we need to update in each iteration, means, the covariance matrices, and the cluster proportions. So X is our input matrix that has 1200 rows and 2 columns. Each of the 1200 points are two-dimensional, and we will try to fit 3 Gaussians. We initialize the parameters, mu, covariance, and pi, and then we start the E step of the expectation maximization algorithm. We discussed that in this E step, we just need to calculate these Rij probabilities, which shows what would be the posterior probability that the point xj would belong to cluster I. And after the E step is done, then using these Rij quantities, we can start doing the M step, where we need to calculate these Wij quantities, and with them we can update the means, the sigmas, and the pi's. After it's done, then we calculate the new log likelihood function and plot the results, and we run this till we converge. All right, so let's run it. We will run 8 iterations, and we want to fit 3 Gaussian components. And let's see the results. So these are the first random guesses. They are not that good, but as you can see, after each iteration, the means and the covariance matrices are getting better and better. And at iteration 4, they are already pretty good. And finally, at iteration 8, you can see that we learned the right covariance matrices, and the means also are placed into the mean of each of these Gaussian components. Also show how the log likelihood function is indeed improving in each step of the EM algorithm till we converge. Alright, so have some fun with this Jupyter Notebook code. If you have any questions, just let me know. And thanks for your attention.